All right, this is part 3 of the QHack series, in which we will be discussing circuit training in Pennylane. So let's just get right into it. We can see that we can jump into the first problem. So we're given a variational circuit and we want to minimize the expectation value. That's pretty much all. So we can see this code is very straightforward. All we have to do is create a device. In this case, it has two wires, which is 2 qubits. We can then create the circuit, which we are given. This variational circuit is given. And then just use a standard gradient descent optimizer. So this is just stochastic gradient descent, but with the parameter shift rule built in Pennylane. And then step with the circuit and the params and continually update it. And then at the output, we will get this optimal value. So we can see that actually what I'm going to do real quick is circuit params. We'll be able to see this minimizing. Oh, I have to cd into this directory. So we should, oh, I just realized I can't see that. There we go. So you can see I'm running my code and for some reason it always loads TensorFlow, but okay, yes, you can see it minimizing. It reaches a minimum of about 0.617. And so we can do type, oh God, what did I do? Okay, there we go. We can do type one.answer and we can see this answer is pretty much the same. So, yeah, I'm going to comment that print statement out in the final submission or when I upload the code to GitHub, just so it's exactly the same as what recreates the QHack solutions. So you can see this one was super easy, just a few lines of code. The second one is a little different. So this one is QAOA based, and I have a video on that, so you're welcome to check that out if you don't know a lot about QAOA. But in this case, it's not max cut QAOA, which is like what everyone does. It's actually maximum independent set QAOA. So it's still a binary optimization problem, which is what QAOA works for. It's just a different Hamiltonian. That doesn't even matter because we don't have to train it. We are given the parameters for a 10-layer Hamiltonian. Or a 10-layer trained cost mixer alternating Hamiltonian. So we're given the optimal parameters, and then we have to tell them the optimal nodes for this solution. And so the way we do this introduces us to Pennylane's QAOA module. So what we do is we instantiate the wires, and so here we can just get the cost Hamiltonian mixer Hamiltonians from the QAOA. It just gives us them from this max independent set. And there's a bunch of different options. There's max cut, there's all these other ones. And so once we have them, we can define the QAOA layer, as alternating cost and mixers. And so from there, we can create the circuit. So we do QML layer, which creates an X number of layers, in this case 10 layers. And our params vector is a 2x10 vector with all the gammas here and all the alphas here. And so this will just handle the layer construction. So then we create the device with the given number of wires. It's the size of the graph in this case that we're given. Just like in MaxCut, the number of qubits are the same as the number of nodes of the graph. And so then we just return the probability of measuring each qubit. And the reason we want to do that is because the most probable string of measurement, remember that's what we're optimizing for in QA, the most probable string will be this maximum independent set. That's the whole point of this optimization. So if we're given the optimal params, we can just run the circuit and then it will give us a bunch of outputs because it's probabilistic. So we want the maximum one. So we sort it, get the last value, and then this is just sort of a leftover. This is just formatting this output because this output is in multi-dimensional NumPy array. So we're just formatting the output. And then remember, we're padding it with 0 because it's only going to give us the output. It might be, if it's 10, it might just give us the output in binary when we want to pad it so that all strings are the same length. So, so if we go back, if this was the output, it wouldn't actually give us this 0 right here. It would just give us, because it's the same number in binary, 0 adds nothing. Depending on how you read it, I guess you could read it right to left, but why would you do that? And so we're just padding basically that 0. And then we get the maximum independent set. So we can see that we can run some examples and we can see that I don't want circuit training 200. We can run that. And so it'll find the maximum independent set of a graph. The graph is provided. We don't deal with that, so we can compare it to the one.answers. I keep doing that. We can see 2, 3, 4 is correct. I can do the same thing actually. And the answer for 2 is 0, 1, 2. And so this is really just an introduction to the QAOA module and Pennylane. So this is probably the least exciting of the challenges. And so now we get into probably what I think is the best challenge of QHack, which is challenge circuit training 500. So I guess I can X out of these. And so this one, they give us multi-class classification. So there's 3 classes that we're assigning a point to. And so we have to assign it to either -1, 0, or 1. And I have no idea what the data even looks like. I'll be honest, I never even plotted it. And so you have to fit 250 points to this training data and then predict on some testing data. And so there's a number of ways that you could do this. This is why I like it, because it's very open-ended. I set the random seed here just to reproduce things, but I can get rid of that. It's not necessary. I just always like to set random seeds when I'm testing machine learning applications, because you'd be surprised how much a random seed can impact things. So you want to know if that a change you made is really because of the random seed or because of an actual code difference you made. So I actually just exactly copied this layer notation from, they have a tutorial on binary classification in Pennylane, and so I just copied their setup there. So we have a given layer. So the general idea that I had was, okay, we have there's 3 points of input, right? Yeah, there's 3 points of input, and we need to predict it to 3 classes. So let's just use the 3 qubits as input. And so I just did angle embedding because they're numerical values. And so you can embed 3 of them in 3 qubits. And so the general setup is that we have the angle embedding, and then we have a certain number of layers. And so each layer has arbitrary rotations. This is just a unitary rotation because remember, it's u of, I don't even remember, theta, psi, or I don't remember the Greek letters they use for angles, but there's 3 rotations that you do to get the unitary rotation, and it's 1 on each qubit followed by 3 entanglement operators. And so then for each, we make a certain number of layers, and then we measure the first qubit. We only measure the first qubit. And so from there, we also add a bias to, just to, I guess I didn't even check if this was necessary, but it's just common practice to, or it can be common practice to add a bias. And so we use mean squared loss, which we just have to code. I really wish, I shouldn't say I wish, they might have this installed, but to the best of my knowledge, they don't have default loss functions built in. And that's kind of a pain because you have to write all this out. Like, I was thinking about doing like sparse categorical cross entropy, but then I'm like, oh, I don't want to do all this by hand and stuff. So it'd be really nice if they had a dot fit function where, in here we're manually sort of doing, we're not even doing apply gradients. We're keeping track of the parameters sort of outside of the circuit, which is kind of annoying at times. But I get why they do it. There are pros and cons, so I don't want to say it's all bad. But anyway, here we do square loss. We can see that the classifier is just the circuit of the given input and the weights plus a bias. And then the square loss is the mean square loss. It's pretty much what you exactly what it is. We have the cost function, which just takes the predictions for some batch X, and then calculates the square loss. And we have accuracy, which just just tells us the accuracy. Once again, having to do this all by hand is kind of annoying when you could just call it TensorFlow Quantum.mse, but that's neither here nor there. And then we define the number of layers. So I just use 3 layers. It just works, so why not? We initialize it to random, and we initialize the bias to 0. We set the atom optimizer. We set the optimizer to be atom with a learning rate of 0.12. The batch size is 10, and here this is a prediction function. So remember, when we measure the output, it's a real number between -1 and 1. And so we have to split that up into 3 equal portions. So if it's greater than 2/3, or if it's greater than 1/3, so between 1/3 and 1, return 1. If it's between 1/3 and -1/3, return 0. Otherwise, return -1. So this just sort of discretizes the output into our desired classes. So we can uncomment this. That way we will be able to watch it as it trains. We get a random batch, so this is mini batch sampling, and then we take one step of the cost function and variables, and then we calculate the accuracy, and if the accuracy is high enough, if you look back at the problem statement, we needed 95% accuracy. So if it's greater than 95, we can stop, because I don't want to overfit the training set. So that's sort of why I put that in there too. And then we make our predictions on the test set, which is not trained on. So we can see this in action, because I don't want to show I'm not going to show the comparison to the actual answers because it's just a very long array, 50-length array of just numbers. But we can see, hopefully, in a second, that this will train effectively. Yeah, so we can see it's not the fastest process, but we can see that over time, the cost decreases and the accuracy increases. So we can just wait a second. Actually, I'll just pause now and you guys don't have to watch it. Okay, it has finished training. You can see it appears as though it only reaches 86% accuracy, but that's actually because I put the break statement before the print statement. So it reaches 95% accuracy, breaks, and doesn't print. That's why it doesn't reach the 95% accuracy, but also it doesn't finish the iterations. And we can see that on the test set, I'm pretty sure this is 100% accurate. Just looking at it, we can see a comparison here of the predictions on the test set, which I believe to be 100% accurate, but you could do a specific comparison if needed. And so that's just one approach, though. You could also have, what I know other people have done is use a single qubit and then just do rotations on there, because we only ended up measuring one. So if we only measure one qubit, then theoretically you could encode the 3 values. There's 3 axes. You could sort of encode it on there, and so that's an interesting idea too. But in the end, this one worked, and so I was content with it. And so we can see that I will remove the print statement from the code just to be exactly replicable. And that's pretty much all the circuit training examples for QHack.